All right, so far you heard about energetic particles in the heliosphere coming from the sun and coming from outer space. But even if Fran has given a very nice introduction, and I saw all her slides about planetary magnetospheres, I will convince you that there is a lot of things which can be done only by energetic particles, or mostly. Okay, so here's the structure of the second part. I will briefly discuss the radiation belts and a little bit about synchrotron radiation, and then we'll show you what the energetic particles contribute in order to get an understanding of the global configuration and the magnetodynamics of the magnetotail in planetary magnetospheres. And especially the last point is something I want to address a little more time on, because I want to show you how the measurements can be used to identify and study plasma processes which you normally cannot directly measure easily in the magnetospheres. This is just an overview of how we think the Jovian magnetosphere looks like, and it's basically what Fran showed already. But I want to address a couple of major points here on this slide again. You see that there is a region inside of the Io torus and also the Europa torus, which is a little fainter drawn here, which is called the inner radiation belts of Jupiter. And as I said before, this is where this grant processes comes in, where cosmic rays populate the inner radiation belts. Otherwise, those particles or those radiation belts would be mostly empty, or at least only with very high energies, populated with higher energies. Then we have this magnetodisk region. This is this co-rotating pancake, I always call it, which is rotating with the planet. And this is where most of the energetic particles are located, near the equator of that rotating system. And in the case of Jupiter, this is also wobbling by plus minus 10 degrees around the orbit of the moons. Then a little further down, you have this plasmoid release of particles where the reconnection process plays a major role, similar to what I showed you for the CME reconnection acceleration mechanisms. Also here, by pinching off plasma in the magnetotail of a planetary magnetosphere, you accelerate particles along the field lines, which then at the end up in the equatorial region along these field-aligned trajectories. And of course, then the moon-magnetosphere interaction, this is something I will address a little more, plays a major role. So energetic particles play a major role in understanding the surface of moons. And, you know, space weather is one thing, but you can also have weathering effects of energetic particles at the moons caused by these impinging energetic particles in the magnetosphere. So the same is true, of course, for Saturn, and this is the current picture we have for Saturn, where also the major source, of course, is also a moon with Enceladus, providing essentially only water energetic particles in the water molecules for the magnetosphere, and they are also co-rotating around the planet, creating very interesting effects in the magnetosphere. And so these two magnetospheres are of great interest in order to understand what's going on in also maybe exoplanetary magnetospheres, because Jupiter and maybe Saturn are sort of templates for all the big hot Jupiters currently being found outside of our heliosphere. And you can already see here on this picture that for Saturn and also for Jupiter, this is true, that we always talk about a region of hot plasma. This is where the energetic particles play the major role. So in this region, the plasma beta, which is the ratio between the particle density and the magnetic energy density, is greater than 1. So the particles play the major role in this region. And then an inner magnetosphere in this ring current region, and inside where the icy moons are located, this is where the low energy particles and also, of course, the neutrals coming off the Enceladus source play the major role. And the interaction between the two is something you can study with energetic particles quite nicely. So just to start with, this is an overview of all the particle measurements we have so far from Galileo measurements at Jupiter in the equatorial plane, and also perpendicular to it, and in the same format what we have from Cassini in Saturn's magnetosphere. And you can immediately see that the color-coded intensity of those particles are different when you go in different locations, in terms of local time locations, and also in terms of radial distributions. So you see inside of the moons here at Jupiter, you see that there's a large increase of particles. These are the radiation belt particles I was talking about. And further out, you see that there is an asymmetry. You see more particles with higher intensities, mainly on the dawn side, on the dusk side here compared to the dawn side. And if you go further out, then the intensity drops down, by a power law distribution, essentially by 1 over r to the third. The same is true actually for Saturn. You see there's a very high intensity region here. Then you see a dropout of particles, and I'm showing you this in more detail. It's caused by the moons and by the neutral cloud present in this region of the magnetosphere. And then inside there's an increase, and this is actually an artifact which is not true. This is what we think is penetrating radiation, which shouldn't be there, but it is measured in the particle detectors, and you have to get rid of it, but you have to know that it is a false signal. So all of this, of course, started with the Earth. If you talk about radiation belts, you're very well familiar how the radiation belts have been discovered at Earth. You see here Explorer 1 with Pickering and Werner von Braun, and of course James Van Allen. They found in their Geiger counter that these dropouts here and then big increases with the saturation effect. And immediately after that, it was sort of the first confirmation that there is a large radiation belt present in the vicinity of Earth. And this is how all this particle detector business started actually from. So how does it look for the outer planets? And this is a very nice summary, which is in a paper by Don Williams in an APL internal journal, where they summarized how the radiation belts look like for the 4 outer moons, for the 4 outer planets. So for Jupiter, these are all Voyager results. So for Jupiter, you see during the flyby, it came in and you see these highly structured plasma sheet crossings when you come in. And then suddenly you see this big bulge of highly energetic particles in the vicinity of the planet itself. And the structure looks a little bit different at Saturn. You see this is this dropout, the increase, and another dropout. You see a dropout here for Uranus, and the same for Neptune. So this is from one single instrument, a measurement of all the 4 radiation belts of the outer planets. And of course, we can do a little better now by looking at Galileo data, by remote sensing, by radio emissions, in order to find out what really the radiation belts of the outer planets look like. And one idea is that you look at this so-called synchrotron radiation, which is caused by about 50 MeV electrons entering into this inner system, get trapped along the field lines, they bounce back and forth, and during their motion along the field lines, they send radio emissions tangentially from the field lines out, and this can be measured at Earth. And actually, this is how the Jovian magnetosphere has been discovered, by looking at synchrotron radiations. So you can make measurements, you can do simulations, and this is what comes out of the simulation results. You see that there is a large portion of synchrotron radiation being emitted in the inner part of the radiation belt, but also near the vicinity of Io here, in this case, with these lobes here extending at higher latitudes. And you can see how this wobbles around, and this is very well documented in the Jupiter book published by Fran. So this is one thing you can do by looking at the radio sources and the synchrotron radiation. But of course, by knowing and having in situ measurements of energetic particles in that region, you can also model those. And this is just one of the best radiation model we have currently. It's a combination of the Devine Garrett and the GEAR model, where here you have a sort of a cut through the radiation belts of Jupiter. On this side, these are the ions, and these are the electrons. And you see here the intensities of 10 MeV particles integral flux on both sides, and 1 MeV integral flux for electrons. And you see that the structure of the radiation belts are different if you look at ions compared to electrons. I think Fran showed this before, so I will not go into the details here. But it's just to show you that there's a lot of high energy radiation being present in the vicinity of the moons, in the inner moons, Io, Europa, Ganymede, and also a little bit further out still for Callisto, which of course you have to be able to identify first, but also to get rid of if you want to do measurements in this inner part of the magnetosphere where you don't want to see the 50 MeV electrons, for example. So coming back to Saturn's radiation belts, now these are real measurements taken by the MIMI instrument on Cassini. And so here it's slightly different compared to Jupiter. You have, of course, the radiation belts itself, but they are somehow interrupted, caused by the moons. So you don't have a continuous emission, a continuous radiation belt as a whole, but there are some gaps in between, and they are caused by the absorption of particles on the surfaces of the moons. And they can be measured, and you can study a lot of very nice and interesting plasma processes by doing so. So the idea is that those particles, they are bouncing back and forth along the field lines, and the moons itself, they of course orbit the planet itself, and whenever such a particle hit the moon, it's lost, leaving a gap behind. This gap is then usually filled again by diffusion processes, but there are some diffusion coefficients, and the number of particles at the end have the results that they have what they call a macrosignature for all the moons. At all longitudes and at all local times, there is a sort of a gap of particles because of the losses onto the moons. So there are other features in terms of Saturn's radiation belts discovered by Cassini, and this is that they are highly variable. And sometimes they even appear a new radiation belt from a transient radiation belt here between the orbit of Dione and the moon of Tethys, which you can see here. There are actually three lines here. There's a white line, which is nearly on top of the yellow line. And these are the normal radiation belt structure of Saturn's inner magnetosphere. And then for some of the orbits of Cassini, when we passed through this region several times, there was an additional radiation belt present, which we call the Dione belt, which lasted only for a couple of weeks and then disappeared again. Of course, we looked at events in the heliosphere, and we found that there were CME hitting Saturn's magnetosphere a couple of weeks before. And then the response of those particles obviously created an additional radiation belt in Saturn's inner magnetosphere, but only until about this point, and no particles were able to make it across the orbits of the moons to get also an effect on the inner radiation belts of Saturn. So this told us already that even if there is a solar wind or heliospheric influence on the structure and the overall configuration of Saturn's magnetosphere, it only is valid until they reach essentially a boundary inside the orbit of Dione, inside the orbit of, between Dione and Tethys. And this is because those particles which are coming in from the outer part of the magnetosphere through such a solar wind effect, they get accelerated, and then they travel radially inward due to violating the third adiabatic invariant. They gain energy when they come in, but at some point they are completely lost because they hit the neutral gas cloud of Saturn's magnetosphere. So they cannot travel further because they are totally lost in the radiation, in the neutral cloud, which is in the vicinity of Enceladus and a little bit outside of the moon itself. So this told us already the inner radiation belt must have a different source. The inner radiation belt, as I told you before, are populated what we think due to these ground processes, which I explained earlier in the morning. Okay, so far we only looked at at the inner part of the magnetosphere, the radiation belt. But of course, there are a lot of processes which you can study with energetic particles when you look in the middle magnetospheres of the outer planets. And this is just to show you this diversity of these interactions, what can happen in Jupiter's magnetosphere, for example. So you have what they call interchange transport motion, where low energy plasma is transported radially outward. You have injection events, which are coupling these hot plasma regions into the inner magnetosphere, where there is only cold plasma present. So there is also some exchange between hot and cold plasma. And then you have all these interaction regions with the moons, especially with the Ganymede, which has a small magnetosphere on its own. So this is a unique place in the solar system where you have a small magnetosphere sitting in a large magnetosphere. Then, of course, the space weather effect on the moons. So the impacting high energy particles onto the moons can also create features on the surface, and also releasing, sputtering, and backscattering particles can be measured in the vicinity of the moons by looking at the energetic particles. And then there's this electromagnetic coupling between the moons and the planet itself, these flux tubes which connect the moon to the auroral region. And of course, these footprints of all the moons can be studied in great detail by looking at the particle distributions as well. So I will go through some of those examples, what can be done with energetic particle measurements. And I will start with these injection and interchange events, which we have found at Jupiter and at Saturn. And they are relatively similar, at least the injection part, relatively similar to these drift echoes in the Earth's magnetosphere. So we have essentially particles coming in from a completely different phase-space density region in the hot plasma regime of a magnetosphere, and they are transported radially inward. At the same time, you have these finger-like structures from the inner part of the magnetosphere, which are transported outward. So if we happened to fly with a spacecraft exactly through these regions, you should see some changes in the overall particle distributions. And this is exactly one of those examples shown here on the right-hand side in the low-energy plasma, but also in the energetic particle events, which are shown down here. So you see that there are changes in the frequency spectrogram. If you look at radio waves, when you cross through one of those fingers, and this corresponds to a larger density, because out of these hybrid frequency, you can determine the plasma density quite nicely. And at the same time, you see changes in the magnetic field configuration, and you see these increases in electrons, energetic electrons in the MeV range. So this told us already there's a lot of dynamic going on in the magnetosphere of Jupiter. And later on, with Cassini at Saturn, we found the same thing. So the idea is, as I said before, there's a hot plasma injection, and due to the drifts of the particles, the gradient B and the curvature drifts of the particles, they make their way all the way around the planet. And if you have a spacecraft located at the right location at the right time, you see these time-dispersed signatures in the energy spectrogram as a function of time. And out of which, from those dispersion profile here, you can determine actually where the particles have been injected and how long they last already. So lifetime plus injection site can be determined. So if you do this and do a sort of a histogram where they have been injected into the magnetosphere, you find that they are distributed all over the place in a rotating system, which is called System 3 in terms of Jupiter and Saturn. But there is some slight indication that there are a few more bigger events here located at a east longitude here on average. So there's something which is still being debated, but with Cassini we also found that most of those particle injections are coming through the tail region, and then they are doing multiple orbits in the magnetosphere, so sometimes it's not easy to distinguish if they have done one or more rotations in the magnetosphere before they have been detected by a single spacecraft in the magnetosphere. So this tells you already, by looking at these dispersion profiles here, you can really find out how dynamic your magnetosphere is, and you can also determine the velocity of your plasma. By looking at the slopes of those injection events here, you can find out what the plasma really, the flow velocity of the plasma was really like at this specific location and this specific L shell, because it has to be the same injection site for all the different energies, and the different energies drift with different velocities in the magnetosphere, so you see them at different times arriving at the spacecraft, but they should all originate at the same time with the same plasma velocity behind. So you can determine the plasma velocity by looking at this. Another interesting feature which has been found associated to these injection events is that sometimes those injection events are also related to additional emissions in the aurora. So this tells you, by looking at multiple instruments, looking at the aurora from Earth, for example, this is an HST image from Earth at the same time when Galileo was in the vicinity or was on a field line which connects you along the field lines to this region here, you can identify that this dynamic event must have caused, most probably, this extra emission in the aurora. So you can really do magnetospheric dynamic in great detail by looking at the energetic particle dispersion events. If you then go further out in the magnetosphere, what we found with Galileo was quite an interesting thing, that by looking at the directional anisotropy of the particles, by being able to measure particles coming from 4 pi in sky with the Galileo instrument, we could identify that along one of those trajectories where you expect that the particles are still at least subcorrotating with the planet itself, that there are some interruptions where most of those particles are radially away or radially towards the planet, with a sort of a periodic behavior of about 2 to 3 days. We found this not only on one event or on one orbit in Galileo, but by looking at other parameters, such as, for example, the spectral index here, which I mentioned before. This is this slope rocking of a power law going back and forth. You see the same behavior, that every 2.5 to 3 days, the spectral index changes. So telling you that something happened in the magnetosphere, even if you haven't seen this burst of particles radially away, because you were on a different location, you see the response of the magnetosphere accelerating particles back and forth at a rate of 2 to 3 days. You have another independent measurement by looking at the radio frequency events, and you see every time you see one of those radially outward bursts, you see also here emission enhancements in this energy range, which correspond to auroral emissions. So this tells me that at least during some of those events, you have been at the right time, at the right location, and you saw these energetic events where there is plasma being ejected down the tail in maybe smaller or bigger plasmoids. During this reconnection of those plasmoids, the particles are accelerated along the field lines, hitting the auroral zone, creating these additional auroral emissions in the plasma wave. If you then go even further down the tail, and I think this was shown by Fran already, you see the same blobs of plasma down the tail at distances of Jupiter's distant tail of 1,500 Jovian radii, also at about a rate of a couple of days. And so this is another indication that you saw these plasmoids, which most probably we have seen with Galileo at about 100 Jovian radii here, or between 80 and 100 Jovian radii. They are still ongoing and are still somehow detectable very, very far down the tail with New Horizons measurements. Energetic particles are also a very useful tool in order to make the invisible visible, and you can use the aurora as a sort of a camera for magnetospheric activity. I told you before that there are these flux tubes connecting you from the moon towards the footprint of the moon into the aurora itself. You see here, this is Io, and this is another footprint. I think this is Europa here, where you always see a bright spot. Most of the time you see a bright spot directly when your magnetic field connects you with the moon. And with Galileo measurements during the flybys at those moons, we were able to show that they are related to field-aligned electron beams going along the field lines back and forth. And of course, the 100 keV electrons is about the energy creating these auroral emissions in Jupiter's magnetosphere. But in addition to that, you can see there is this main auroral emission. And Fran told you already that this is caused by the so-called co-rotation breakdown region of Jupiter's magnetosphere. This is where the planet is not able to maintain the friction, so to speak, to co-rotate, the plasma co-rotate completely with the planet itself, so it breaks down and lags behind the rigid co-rotation, creating field-aligned currents, creating these very nice auroral images of the main oval. And in addition, you have polar emissions, and polar emissions means that they map poleward of the main auroral oval, meaning that they map out to distances very far down in the tail of 100 Jovian radii, or even further down the tail. And some of those particle emissions are also already in the polar cap of open field lines. So the plasma processes near the moon play a role, of course, near in the aurora itself, but also on the other side as well. And this is a very nice picture here where it is shown that the particles here coming along the field lines towards a moon, it could be Io, it could be any other moon, where there's, if they have an atmosphere, there's a sort of atmospheric sputtering going on, but some of them also make it all the way to the surface itself and sputter material off the surface. So when you have an instrument where you can measure the incident particles, the energetic particles, the MEV particles, as well as those particles released from the surface or from the atmosphere, you can do a sort of a remote sensing of the surface or of the environment of a moon by just looking at the particle distributions. You don't need an infrared spectrometer to say something about the surfaces. Of course, it's a much better instrumentation to do so, but you can also find a lot of information by just looking at the particle distributions. I mentioned a very special place in the magnetosphere of Jupiter and in the entire heliosphere is the Ganymede magnetosphere sitting inside the Jovian magnetosphere. And this is where a lot of other additional aspects of particle motion and particle dynamics takes place. You can see that there are closed field lines, there are open field lines, and exactly at the boundary between open and closed field lines in Ganymede's magnetosphere, there's also an aurora at Ganymede present, which is shown here in this very nice image here. So with JUICE, with the new European mission to Jupiter for the younger generation from 2030 on, we will be able to fly through that region multiple times, go in and out of the magnetosphere, and will stay in orbit around Ganymede's magnetosphere in order to find the characterization here quite nicely of what this region of the magnetosphere looks like. And this brings me already to the last section of this energetic particle lecture. What it can be used for to find out unknown things before. And I've listed only a couple of them. I'm sure there are more, but one of the most important things is that with looking at the particle distributions, dropout signatures, or changes in the orientation of the plasma, you can find out and can identify new unknown objects. And this happened several times already by just looking at the particle distributions, where there have been a new ring found in the magnetosphere of Saturn. There are ring arcs, there are neutral clouds like the Europa torus cloud, and also, as I showed you before, an additional radiation belt, which was not shown before. You can determine diffusion coefficients. You can determine the flow velocities. Recently, we have found an unknown source of an electric field in Saturn's magnetosphere by looking at the variations of the particle distributions. I'll show you one example there. You can determine the open-closed field line boundary if you have the opportunity to look in two directions, along and against the magnetic field direction. I'll show you one result of this. Surface weathering I mentioned already, and also global imaging by using the ENA principle in order to get a better understanding of the global picture of the magnetosphere. So let's start with the discovery of the Europa torus, and this is one of my favorite subjects because it has been identified by looking at pitch angle distributions of energetic particles, which was by some referee not accepted because there was no image present. And the image was of the Europa torus was then later shown by an ENA image from the Cassini flyby at Jupiter, and then it was confirmed that there has to be a Europa torus neutral gas cloud along the orbit of Europa. But originally, and this paper was rejected before the image of Cassini was then later being done, we saw that in the energetic particle pitch angle distributions of a given energy here, we saw a dropout at about 90-degree pitch angle, while for other energies higher up, we saw a sort of a trap distribution where most of the particles have a 90-degree pitch angle distribution. So this told us already in this energy range, there is something which prevents particles to bounce all the way up and down along the field line, and only those particles with 90 degrees are somehow lost. So from that dip of the pitch angle distribution, we could determine that there must be something in the way of the particles along their bounce motion up and down, from which we could determine that there has to be some sort of a neutral cloud with a density of about 50 per cc in the vicinity of Europa. And that's exactly what later on the ENA imaging results showed, that there is such a torus present all the way around the Europa. Another discovery of Cassini is that we have found an additional radiation belt inside the main rings. It's inside the D-ring, it's the innermost ring, the visible ring of Saturn. And we used, again, this principle of the ENA measurement technique to find those, because so far Cassini has not passed directly through that region. It will at the end of the mission. It will go directly through that radiation belt. But during the first orbit, the insertion orbit at Saturn, in the ENA camera range, we saw an emission of particles coming from that region inside the D-ring. Before, we couldn't see that because all the radiation belts were always in the field of view of the NCAR camera, and most of the ENAs we saw were coming from this interaction between the neutral cloud and the charged particle population. But during the insertion orbit, we were inside this major radiation belts. We were inside the neutral cloud, and we could look along the field of view of the camera, of the ENA camera, towards the planet, and we saw an extra emission coming from that region, from which it has been determined that it has to be a sort of a charged particle radiation belt inside this D-ring. And at the end of the mission, in 2 years from now, or 3 years from now, Cassini will fly through that region directly, and we can do the measurements directly. Another thing which you can do very nicely by looking at particle distributions is look at absorption signatures due to moons or ring material or neutral torus, and you try to identify how long it takes to fill up this gap again. So by looking at various locations relative to the object which caused the absorption, you can find out a sort of a diffusion coefficient by looking at the profile of this absorption. So what is shown here is simply, here is in that case it's the moon Tethys, which prevents particles of being going up and down the field line around the moon. Some of them are lost, so you see the normalized intensities in an electron range, which is listed here, 40 to 60 keV. You can just map this and just find out due to this curve here and put it into an absorption distribution function, that it has to be something which is caused by the moon itself, and it is refilled at a rate which is given by this radial coefficient, the diffusion coefficients, which you can determine by simply the slope, which is coming out of that determination, the slope between this radial diffusion coefficient as a function of L. You can determine for several parameter of the exponent of this L dependence of this radial diffusion coefficient. You can determine the diffusion coefficients in the magnetosphere of Saturn, and you are not able to do this without energetic particle measurements there if you do not have an extra instrument to measure this. I mentioned that we can also determine flow velocities out of our directional information, and this is just an illustration of what has been done with the Galileo data, where we have, as I showed you before, we have an intensity profile, which is a power law. You can just into the first order find out that this intensity is a function of the flow velocity and the cosine of your look direction. And by knowing and by having different energy channels and different species you can look at, you look at the first order anisotropy, which usually has a couple of components, the flow anisotropy and the gradient anisotropy. But by looking at different species and different energy ranges, you find out that they're all the same, from which you can determine the flow velocity alone. So there are no gradients present which make an anisotropy measurement, but only the E cross B drift, which is mass and species independent, is the drift velocity which creates the measurements, out of which you can then determine from those anisotropy measurements, by knowing the spectral slope of your measurement, you can determine the flow velocity, and this has been done along the entire orbits of Galileo. Characterization of electric fields. I mentioned this before, that this is a new result from Cassini measurements. It is published in a JGR paper, in Icarus paper actually, that we have looked at those absorption signatures due to some of the moons. In this case, this is Tethys. And this is where you have expected that the absorption signature should have been. So by the displacement, this offset between the signature where you see it and the expected signature, you can determine that the entire magnetosphere has been stretched or has been somehow compressed at the time of the measurement. If you then do this for a lot of measurements where you crossed the L shell of the moons, and you know where the moon was with respect to the signature you see, then you find out that this displacement in L, so this offset, as a function of local time, shows this structure here, that it is inward displacement on the night side, which is around 0 or 2400 hours, and it is a radial outward displacement on the day side, around noon. And the only way to explain it, if it's not a magnetic field effect, and we could rule it out, is that there is an additional electric field in the noon-midnight orientation present in Saturn's magnetosphere. And it's currently a big discussion going on where this comes from, and no one has a good answer yet. But it is something which is coming out from energetic particle analysis. Another feature which is very successfully used at the moment for Cassini results is to determine where the open-closed field line boundary of the aurora is. It's different from Jupiter, that you have a co-rotation breakdown at Jupiter creating the main auroral oval. At Saturn, it's mainly similar to the Earth's aurora, where the main oval is created in this region where an open-closed field line boundary is. So an open-closed field line boundary where the particles can enter into the auroral region creates the auroral emissions there. And you can find out this if you have a detector on board a spacecraft looking along and against the magnetic field direction. And this is shown here. So they are about the same energy ranges. One detector is looking along the field line. The other one is looking against the field line. And they match quite nicely all the way until about this position here, when suddenly you see much more particles from one direction compared to the other. So if the ratio is plotted here, if the ratio is around 1, this tells you that particles are bouncing back and forth along a closed magnetic field line. So you see the same particles in one direction compared to the other direction. But if you are on an open field line, you lose this connection to one of the ends, and you see only the particles coming from one direction only. They're not going back into the other direction. So this tells us that you have crossed the boundary between a closed field line and an open field line. By doing this and mapping this into a magnetic field model, you find out where your open-closed field line is, and you can map it then down onto the aurora, and you will find the main oval of the Saturn aurora quite nicely. The last 2 points I'm going to show is this interaction between the magnetosphere and the moons. And this is just to illustrate how if you have a moon and you have these 3 different types of motion in the magnetosphere, so it's the bounce motion, the gyration, and of course the drift motion, there is one energy where at a given distance where the moons do not see the bouncing particles. So this means the motion of the moons is just that during one bounce motion back and forth, they will just not see the moon as it is. And this energy is called the resonant energy. Anything which is below that energy is impinging the moon from one side. Anything above this energy is impinging the moon from the other side. So this is used here to find signatures of surface weathering on the moon's surfaces. And this is illustrated here in this very nice cartoon. Here on the right-hand side, this is what I just said for different pitch angles and different energies and species. Actually, you see where the resonant energy is, where the particles are suddenly coming from the other direction. And this is illustrated here in this image here as well. So you see the cold plasma is coming from this side, and the energetic electrons above this so-called resonant energy is coming from the other side. And this is creating a sort of a lens-like feature on the surface of the moons. In this case, I think this is Tethys or Europa. I forgot actually what it is, which tells you that the energetic particles create these albedo changes on the surfaces of the moon. So you need to know how much of those particles in various energy ranges are impinging on the moon's surfaces, and you can determine what causes these albedo changes. It could be backscattered or sputtered particles from the surface. It could be particles which are somehow implanted onto the surfaces, changing the albedo of the various moons. This is something similar to this slide here, where we try with JUICE. This is one of our goals, which we will hopefully manage to tackle with the JUICE project and our instrumentation on board, that you can determine remotely if there is an exosphere or if there is some backscattered ENA or sputtered neutrals coming off the surface by looking at all the energy ranges at the same time. So you have the possibility with this instrument to look at the impinging and the incoming particle population, but also those which are released from the surface, out of which you can determine what the surface composition might be of this moon. I will end the presentation here by showing you 2 movies. One about the global imaging of a magnetosphere by using this ENA concept. So what you see here is a projection of the ENA emission seen by the INCA camera in the Saturnian magnetosphere. And in addition, you see here also the radio wave profile as a function of time. So you see here, this is Saturn in the center with the rings. These are the moons, various moon orbits. This is the orbit of Titan. And what you see here is simply, I have to restart this again. You simply see here that at a given time, the ENA emission suddenly enhances by several orders of magnitude, and this entire blob of emission is moving around the magnetosphere with nearly the co-rotation velocity. At the same time, you see that the radio wave instrument on board has also enhanced emissions there. So this is the first ever global configuration map, so to speak, or an image, a movie of what is going on in the ring current region of the Saturnian magnetosphere. And we hope that we can do the same thing by applying this principle on the JUICE mission with this instrument, which will be provided by APL again, where we will fly through the Europa cloud, the neutral cloud of the Europa torus, during the inner magnetosphere portion of the trajectory of JUICE. And you will see these kind of emissions there. There will be also some blobs going around here because of the charged particle population, the co-rotation of the magnetosphere. And when you enter it, you will be able to really map out the entire ring current region and the Europa torus density and things like that when you fly through that with an ENA type of an instrument. So this brings me to an end. And I will summarize by saying that the energetic particles, of course, play a major role in the heliophysics in all kinds of various applications. And they are a very useful tool to determine a lot of parameters which you are not able to directly measure easily on spacecraft. Thank you very much. And before I show you the thank you slide, this is my acknowledgement section, because a lot of stuff which I showed is coming from a lot of people, and part of them are listed here. If you have any questions, please do so. Thank you very much. Questions?
So you present a lot of in situ measurements, but I'm wondering, what are the limitations of ground-based radio observations in this field? Where, like, how far can you get with that stuff?
Yeah, this is a good question, actually. I mean, ground-based observations have been done through Hubble, for example, which is a great help in interpreting the Cassini and Galileo data. So this can be done until Hubble will go down. I don't know when it will end, but it will end at some point, and the other James Webb, or what is it called, will not be there. It's useless for the UV anyway. Okay. The other thing is the synchrotron radiation. So these emissions there. It's not easy to find a good signal from Saturn already from Earth. And of course, for the most outer planets, it's also not an easy task to do it from Earth. You can do it from a spacecraft, but the atmosphere is preventing you from a lot of those measurements already. So it is somehow limited. Of course, you have a lot of other possibilities which have nothing to do with the energetic particles, but you can do, even with small telescopes, and this is being done from PSI, for example. They look for the Io torus continuously for months, and is trying to find out if there are variability in that kind of time ranges. And of course, with the new technology telescopes, you will be able to do a lot of remote sensing from aurora, but also from the cloud structure of the planets. But from the magnetosphere itself, other than looking at the aurora, you have to go there and do in situ measurements.
There are actually very good infrared observations you can do with a telescope. So the IoT
Yes.
look at, not just look at the auroral shapes and variation in time, but you can do Doppler shift. It will give you the motions in the ionosphere.
Exactly, yeah. Mm-hmm.
Look at the Earth. Radar is very important for looking at the motions in the ionosphere. And so the whole business of understanding, motivating the Dundee cycle and convection and motions in the Earth, a lot of that came from looking at
Radio will be tomorrow, yeah.
The radio observations of the motions in the ionosphere.
Yep.
So, you know, then you think about, well, what about other planets? You see these planets, and you can use the infrared, the aurora is a bright emission of the infrared, and you can do Doppler shift. If you have a good enough telescope and get time on it, you can actually see by putting a slit across and measuring the Doppler shift that tells you how the motions are. And last week there was a presentation of this magnetosphere planet.
There has been a big campaign.
Basically now it's proving that the ionosphere rotates the planet rather than
Yep.
showing a downward rotation.
Yes, and these were coming out from Cassini plus ground-based measurements at the same time. So there was a big observation campaign, auroral observation campaign, going on in April and May of this year by using HST, and I think RTF was also involved. Yes, plus Cassini measurements in the UV and also in the infrared. So you can do something remotely as well, but yeah, something about dynamics can be done, but if you want to know the plasma composition somewhere other than measuring in situ, is not an easy task, other than just that particular molecule or atom creating your aurora.
What you're forgetting, Norbert, you have to be a bit careful, because remember, we actually detected the magnetosphere of Jupiter before Van Allen sent those aurora up.
Yes, of course, by using the synchrotron, the radio. Yeah, I mentioned. Yes, of course. But you didn't know what kind of particles are there. You only, found that there is a magnetic field present.
Well, you knew there were electrons because they were.
Yes. And of course, the X-ray is another thing which you can have a look at from Earth. Chandra observations, for example, showing, periodicities of 40 minutes in the Jovian aurora, for example, which most probably come from oxygen 40, 50 MeV. So there's something you can do with remote sensing as well in terms of particles, but not the details.
So, there's no doubt that
The combination.
space.
Okay.
Any other questions?